So here's a question that should keep you up at night. What if right now, at this very moment, an alien spacecraft is cruising through our solar system, taking notes on us like we're some kind of cosmic zoo exhibit? Sounds like science fiction, right? Well, buckle up because we need to talk about something that's happening literally as I speak. There's an object out there, they're calling it Atlas, and it's flying through our solar system in a way that's making some very serious scientists very nervous. Now, before you roll your eyes and click away thinking this is another conspiracy theory video, let me tell you who's making these claims. His name is Avi Loeb, not some random guy with a YouTube channel and a tinfoil hat. This is the chairman of the astronomy department at Harvard University. Yeah, that Harvard. The guy's credentials are so impressive they could fill their own book. And Loeb, he's looked at this Atlas object and identified count them, six characteristics that suggest it might be artificial. As in built by someone, as in not natural, as in, you see where I'm going with this? Here's what makes Atlas so weird. First off, it's fast, really fast. It came screaming into our solar system with the kind of velocity that makes scientists double check their math. But speed alone? That's not the weird part. The weird part is the angle. This thing flew in, almost perfectly aligned with the plane where all our planets orbit. Now think about that for a second. Our solar system is basically a flat disk with planets going around the sun like a cosmic merry-go-round. Everything stays roughly on the same level, right? That's just how gravity works when you've got a bunch of stuff spinning around a central point. But space is three-dimensional, infinitely three-dimensional. An object coming from another star system could approach from literally any angle. Above, below, sideways, the odds of it randomly coming in level with our planetary plane are, well, they're not great. It's like throwing a frisbee from a mile away and having it perfectly thread through a horizontal mail slot. Could happen? Sure. Likely. That's another question entirely. And here's where it gets even more interesting. Atlas didn't just fly through at the right angle, it flew through in such a way that it had opportunities to pass by multiple planets. Mars, Venus, potentially Earth. On October 3rd, it made a close pass by Mars, and we've got robots there. Orbiters, rovers, the whole setup. They're photographing this thing as we speak, data streaming back to Earth. Now, Loeb, and remember, this is a Harvard Astronomy Department chair, not some random blogger. Loeb says, what if this isn't random? What if this is a spacecraft and it's doing what spacecraft do? It's doing gravity assists. It's using the gravitational pull of planets to slingshot itself around, changing course deliberately. See, when we send our own probes out into the solar system, we use this trick all the time. You fly close to a planet, use its gravity to whip yourself around and accelerate in a new direction, saving fuel. It's brilliant engineering. The Voyager probes did it. New Horizons did it. It's how you tour the solar system on a budget. So Loeb's sitting there going, this thing is passing by planets at angles that would allow it to pull these maneuvers. What if it suddenly turns toward Earth? Now, I know what you're thinking. This sounds crazy, right? And honestly, most of Loeb's colleagues think he's gone a bit, let's say, adventurous with his interpretations. When his name comes up in scientific circles, you see a lot of professional smiles and polite coughs, the kind of reaction you get when your uncle starts talking about his investment opportunities at Thanksgiving. But here's the thing, and this is what makes this whole story so fascinating. Loeb isn't wrong about the facts. The object exists, the trajectory is real, the unusual characteristics are documented. Where scientists disagree is on the interpretation. Is it weird? Yes. Is it alien? Well, that's where things get spicy, and Atlas isn't even the first time this has happened. Oh no, this is actually the third interstellar visitor we've detected. The third, which means either the universe is busier than we thought, or we just got really good at noticing things that were always there. We'll get to the others, including one that really started this whole controversy. But first, you need to understand something important. Until about 8 years ago, we wouldn't have even seen these things coming. We were basically blind. But then something happened in 2013 that changed everything. February 15th, 2013, Chelyabinsk, Russia. It's a cold morning, people are going about their business, and suddenly the sky just explodes. A meteor, nobody saw it coming, nobody had any warning, comes screaming through the atmosphere at over 40,000 miles per hour and detonates with the force of about 30 Hiroshima bombs. The shockwave blows out windows across the city. Over 1,500 people are injured, mostly from flying glass. Dashboard cameras, because this is Russia and everyone has dashboard cameras, capture this absolutely apocalyptic scene of the sky lighting up like someone just detonated a nuclear weapon overhead. And you know what the scary part was? We didn't see it coming at all. This thing was about 60 feet across, weighed around 10,000 tons, and our entire global detection network just missed it completely. It came at us from the direction of the sun, and we were blind. That was the wake-up call. That was the moment when governments around the world went, oh no, we need to fix this. Today in Chelyabinsk, tomorrow in Moscow, next week in New York City, because here's the uncomfortable truth. Space is full of rocks, and some of them have our name on them. So starting in 2013, money started flowing, real money, into programs specifically designed to find and track near-Earth objects, and not just near-Earth, and anything that might be remotely dangerous or interesting got added to the watch list. They started building networks of robotic telescopes, autonomous systems that scan the sky continuously, automatically flagging anything unusual. These aren't your grandfather's telescopes where some graduate student sits in a cold dome all night, manually logging observations in a notebook. No, these are AI-powered, computer-controlled survey systems with wide fields of view, taking hundreds of thousands of images every night, running algorithmic detection software, basically turning the entire visible sky into a 24/7 surveillance system. And it worked. By around 2015 to 2017, we'd essentially made ourselves sharp-eyed, as one scientist put it. We went from missing 60-foot rocks to being able to track objects the size of a small car from millions of miles away, which brings us to October 19th, 2017. A robotic telescope in Hawaii, part of the Pan-STARRS survey system, flagged something unusual, something that shouldn't be there, an object moving too fast on the wrong trajectory, coming from the wrong direction. They call it Oumuamua. In Hawaiian, it means scout or messenger from the distant past, and this thing broke every rule we thought we knew about what visits our solar system. Oumuamua is absolutely bizarre from the moment we spot it, and I mean bizarre in ways that make scientists deeply uncomfortable. First off, the shape. When they finally get enough observations to calculate its dimensions, they realize this thing is shaped like a cigar or a needle, or if you want to be dramatic about it, like something you might design if you wanted to minimize drag while moving through interstellar gas and dust. It's about 400 meters long, but only about 40 meters wide. That's a 10-to-1 length to width ratio. Now we've discovered literally millions of asteroids in our solar system. Millions, and you know how many of them have that kind of extreme elongation? Zero. None. We've never seen anything like it. Asteroids are generally potato-shaped, maybe a bit lumpy, but nothing like this needle configuration. Strike one for the "this is just a normal space rock" hypothesis. But the shape? That's just the beginning. The really weird stuff happens after Oumuamua whips around the sun and starts heading back out of the solar system, because it doesn't slow down the way it should. See, when you're leaving the sun, you're climbing out of its gravitational well. You should decelerate in a predictable way. We've got the math down cold. It's basic orbital mechanics that we've understood since Newton. You calculate the sun's mass, the object's distance, run the numbers, boom, you know exactly how fast it should be going. Except Oumuamua doesn't decelerate as much as it should. It's like it's got a little extra push. Something is accelerating it ever so slightly away from the sun. Now here's where most scientists go, okay, it's a comet. Comets do this all the time. They get close to the sun, ice starts vaporizing on the sun-facing side, creates jets of gas that act like tiny rocket thrusters. Mystery solved, except there's no tail, there's no coma, there's no outgassing that we can detect. It looks like a rock, acts like it has a rocket engine, but looks like a rock. This is when Avi Loeb enters the picture, and Loeb looks at this data and basically says, what if it actually is a rocket? What if this is technology? His theory, maybe it's a light sail, a giant, extremely thin reflective surface that's being pushed by solar radiation pressure, photons from the sun hitting the surface and giving it a push. We've actually proposed this as a propulsion method ourselves, using giant mirrors to catch sunlight and accelerate spacecraft. It's real physics. If Oumuamua is a light sail, maybe damaged, maybe derelict, maybe deliberately sent, that would explain both the shape, you want a large, flat, elongated surface to catch maximum photons, and the acceleration. Sunlight is pushing it. And when Loeb published this hypothesis, the scientific community collectively clutched their pearls. You could practically hear the gasps. A Harvard astronomer suggesting alien technology in a peer-reviewed journal? The audacity. But here's the thing, Loeb isn't saying it's definitely aliens, he's saying we can't explain it with conventional models, and artificial origin is a hypothesis that fits the data, which is technically valid scientific reasoning, even if it makes people uncomfortable. Most of his colleagues prefer more exotic natural explanations. Maybe it's a fragment of a planetary collision with unusual composition. Maybe it's a hydrogen iceberg, frozen hydrogen that would outgas invisibly. Maybe it's a dust bunny held together by weird forces. They'll accept almost any natural explanation, no matter how contrived, before they'll seriously consider the artificial one. And you know what? I get it. Extraordinary claims require extraordinary evidence. Its aliens should always be the last explanation you consider after you've exhausted everything else. But the evidence we got was frustratingly limited. Oumuamua came at us from the direction of the sun, which means we were blind to it until it had already passed Earth and was heading away. By the time we realized what we were looking at, it was already leaving. We had maybe a few weeks of decent observations before it became too faint to see. Even with our best telescopes, we weren't ready. We had no deep space probes positioned to intercept. No high-resolution imaging system close enough to get detailed photos. It was like spotting Bigfoot for 3 seconds in your peripheral vision. You saw something, but good luck proving what it was. And then Oumuamua just left. It's out there right now, getting fainter and fainter, carrying its secrets with it. But the story doesn't end there, because in 2019, we got visitor number 2, and this time we were ready. August 30th, 2019, an amateur astronomer named Gennady Borisov, working at the Margo Observatory in Crimea, spots something new. He's using a telescope he built himself, and isn't that just perfect? Sometimes it's not the big fancy institutional instruments that make discoveries. It's one dedicated person with homemade equipment and sharp eyes. He flags an object that's moving strangely, files a report, and within days, other observatories confirm it. We've got another interstellar visitor. They name it 2I/Borisov, the 2I meaning it's the second confirmed interstellar object. Oumuamua was 1I. And this time we got lucky. We spotted it while it was still approaching the inner solar system, which meant we had months to study it instead of weeks. Every major telescope on Earth and in space turned to look at this thing. So what did we find? Well, it's a comet, just a regular comet. It's got a tail, it's outgassing visibly. It's made of ice and rock, probably formed in some other star system and got kicked out billions of years ago, and now it's passing through our neighborhood. It's absolutely, completely, boringly normal. Well, as normal as an interstellar visitor can be. The science is fascinating, analyzing the composition of material from another star system, but there's nothing mysterious about it. It follows all the rules. It behaves exactly as expected, which if you're Avi Loeb is kind of disappointing. But if you're most of the scientific community, it's reassuring. See, they say, interstellar objects are just space debris, natural phenomena, nothing mysterious going on. And then July 2025 happens, object number 3, Atlas 1. So it's July 1st, 2025, just a few months ago, and the detection networks pick up something new, another interstellar visitor, and they designate it Atlas. This time, unlike Oumuamua, we catch it on the way in. And immediately something's weird about this one. It's moving fast, really fast, even for an interstellar object. And the trajectory, we already talked about how it came in almost level with the planetary plane, but there's more. It passes close to Mars on October 3rd, close enough that the spacecraft we've got there, orbiters with cameras, rovers with instruments, can actually photograph it. We're getting actual data, not just distant observations. Then it's going to pass by Venus. Not as close, but close enough. Then it'll pass by Earth, though unfortunately, from our perspective, the sun will be in the way, so we'll have limited viewing. Like Oumuamua, it's timing its Earth encounter in a way that makes it hard for us to see, cosmic bad luck, or something else. Then out toward Jupiter. Avi Loeb looks at this trajectory and immediately starts running calculations. These aren't random flybys, he says. Look at the geometry. This object is positioned to potentially perform gravitational assists at multiple planets. If it wanted to change course toward Earth, there's a window where it could do exactly that using Mars or Venus gravity. And then there's the appearance. Atlas has developed a gas envelope around it. It looks like a comet complete with a tail. See? Say the skeptics. It's outgassing. It's a comet. Mystery solved. Can we move on now? But Loeb points out something odd. Despite looking like a comet, despite having this gas cloud around it, Atlas is flying like a rock. Its trajectory isn't being affected by the outgassing. When comets heat up and start venting gas, those jets act like little thrusters. They make the comet tumble, change its spin rate, slightly alter its trajectory. It's called non-gravitational acceleration, and every comet does it. Except Atlas. Atlas has a tail but flies like it's on rails. Perfect gravitational trajectory, no wobbling, no deviation. So Loeb's argument is, what if the gas cloud is camouflage? What if something artificial is disguising itself as a comet to avoid suspicion? He literally uses the word mimicking. Now, most scientists think this is ridiculous. The more mundane explanation is that maybe the outgassing is so weak or so symmetrical that it's not creating significant thrust, or maybe our measurements aren't precise enough to detect small deviations yet. There are natural explanations that don't require invoking alien spacecraft playing cosmic hide-and-seek. But Loeb has doubled down. He's identified what he calls 6 signs of artificial origin. 1, the high velocity. 2, the trajectory aligned with the planetary plane. 3, the timing of planetary flybys. 4, the appearance of outgassing without corresponding trajectory changes. 5, the approach angle that maximizes planetary encounter opportunities. 6, the fact that we're seeing these objects more frequently now. Maybe they're noticing that we're finally able to notice them. That last one is kind of chilling when you think about it. And you know what? The scientific establishment is taking this one more seriously than they took Oumuamua. Not because they believe it's aliens, most don't, but because we actually have time this time. Atlas is still here. It's still observable. We have months to study it, not weeks. Every major observatory is pointed at this thing. The data is pouring in. And the space agencies are even talking about a contingency plan, keeping a probe on standby in orbit, ready to launch toward the next interstellar visitor whenever it shows up. Kind of like leaving your car packed and ready for a road trip. You don't know when you're going, but when the opportunity comes, you want to be ready. But here's where Loeb's story gets even more interesting, because he hasn't just been theorizing. He's been actively hunting for evidence. And in 2019, he thought he found some. So after Oumuamua, Loeb gets obsessed, and when a Harvard astronomy department chair gets obsessed, he has resources. He starts digging through archives, looking at records of objects that have entered Earth's atmosphere over the years. And he finds something interesting, a meteor from 2014 that hit Earth's atmosphere with extraordinary velocity. Too much velocity to be from our solar system. The speed suggests it came from beyond, another interstellar visitor, but this one didn't pass by like Oumuamua. This one ran straight into us. It entered the atmosphere over the Pacific Ocean, specifically over waters near Papua New Guinea, and disintegrated at altitude. The fireball was detected by U.S. government sensors. Yeah, the military tracks stuff like this, which should tell you something about how seriously they take potential impacts. Loeb traces the trajectory backwards and calculates where the debris would have fallen: deep ocean about 3 kilometers down, and he thinks, what if we could recover pieces of it? What if we could actually get our hands on material from another star system? So what does he do? He charters a boat. Yeah, really, he gets funding, hires a yacht, assembles a team, and they steam out to the middle of the Pacific Ocean with magnetic dredges. They're going to literally drag magnets along the ocean floor and see what sticks, and you can imagine the jokes. Harvard astronomer goes treasure hunting for alien spacecraft debris. It sounds like a National Enquirer headline, but Loeb doesn't care. He's all in at this point. They spend weeks out there dredging, and they find spherules, tiny metallic spheres about 1 millimeter across. They pull up hundreds of these little balls from the ocean floor, right where the calculated debris field should be. Loeb brings them back, has them analyzed, and announces the composition is unusual. These metallic ratios don't match any known human-made alloys. The isotopic signatures are strange. He publishes papers suggesting these might be fragments of interstellar technology, maybe even parts of a spacecraft that malfunctioned, hit our atmosphere, and broke up. The scientific community's reaction, let's just say, skeptical. Other researchers point out that metallic spherules on the ocean floor aren't that unusual. Ships have been dumping industrial waste for centuries. Undersea volcanoes create weird metallic deposits. The ocean floor is littered with odd metal bits. As for the unusual composition, show us isotopic ratios that definitively prove extraterrestrial origin, they say. Show us something that can't be explained by terrestrial processes. And so far, Loeb hasn't quite cleared that bar. But here's what I find interesting about this whole saga. Loeb isn't just making claims and walking away. He's doing actual field work. He's collecting physical samples. He's running tests. He's publishing data. Other scientists can check his work, critique his methods, run their own analyses. That's how science is supposed to work, even when the hypothesis is unconventional. You don't just speculate. You gather evidence, present it, and let others evaluate it. Is Loeb right? I honestly don't know. The odds are probably against him. The "it's aliens" explanation usually doesn't pan out. But is he doing science? Yes, unconventional, audacious, career-risking science, but science nonetheless. And you've got to kind of admire the commitment. This guy went from respected academic to that eccentric professor who thinks everything is aliens. He's risking his reputation, his credibility, his legacy. Why? Either he genuinely believes he's on to something profound, or he's gone a bit off the rails. Time will tell. But while we're talking about alien visitors, let's address the obvious question. Forget mysterious objects flying past us. What about life actually existing somewhere in our own solar system? Because if we can't even find microbes on Mars, what chance do we have of finding intelligent civilizations around other stars? Let's talk about Mars. Mars, the planet that's been teasing us with the possibility of life for over a century, and I mean literally teasing us. It's like Mars is playing hard to get. Let's start with the biggest tease of all, the canals. Back in the late 1800s, reputable astronomers with good telescopes, when we're talking professionals, not cranks, started reporting these linear features on Mars channels, networks of straight lines crisscrossing the surface. The Italian astronomer Giovanni Schiaparelli made the first detailed maps, calling them canali, which means channels in Italian, but got translated to English as canals. And canals are artificial. Canals are built by someone. Then Percival Lowell, American astronomer, wealthy guy, smart guy, built private observatories specifically to study Mars. And he didn't just see the canals, he mapped hundreds of them, drew incredibly detailed charts, published books arguing that Mars had an advanced civilization struggling with a dying, drying planet, building massive irrigation systems to transport water from the polar ice caps to the equatorial cities, and people believed it. This wasn't fringe stuff. This was mainstream scientific discussion in the early 1900s. The idea of Martians wasn't science fiction, it was presumed fact. Then we got better telescopes and spacecraft, and whoops, no canals, none, zip, zero. Mars is covered in craters and valleys and ancient dried riverbeds, but no straight-line canal networks. So what were they seeing? Nobody knows for sure. Maybe some combination of real geological features, optical illusions, and the human brain's tendency to see patterns that aren't there. Maybe the blood vessels in their own eyes projected onto the image, or maybe just wishful thinking made visible. But the canal story teaches us something important. We really want to find life on Mars. We want it so badly that for decades, serious scientists convinced themselves they were seeing evidence of civilization. Fast forward to today, no canals, but we found something potentially more interesting: methane. Methane in Mars's atmosphere, and on Earth, methane comes primarily from biological sources: bacteria in soil, in water, in animal digestive systems. It's a biosignature, a sign of life. Now, methane can also come from geological sources, volcanic activity, chemical reactions in rocks, but Mars isn't volcanically active anymore, so where's the methane coming from? And here's the really interesting part: the methane levels change seasonally. They go up and down. If it was just leaking out of rocks, you'd expect a steady level, but seasonal variation, that suggests something responding to environmental changes, something active. The surface of Mars is sterile. We know that now. The atmosphere is thin, offering almost no protection from solar ultraviolet radiation and cosmic rays. It's a radiation bath up there. Nothing could survive on the surface for long. But underground, that's a different story. Just a meter below the surface, you're shielded from all that radiation, and we've detected what might be liquid water below ground. Not pure water, probably briny, salty stuff that stays liquid even in the cold. But life can handle brine. We've got microbes on Earth living in concentrated salt solutions that would kill almost anything else. So the current thinking is, if there's life on Mars, it's underground, living in aquifers, in caves, in pockets of liquid water beneath the frozen surface, surviving on chemical energy from rock-water interactions, metabolizing in the dark, occasionally burping methane up through cracks to the surface. And we've actually seen liquid water emerge on the surface. Well, kind of. There are these recurring slope lineae, RSL for short, dark streaks that appear on slopes during warm seasons and fade during cold seasons. They look exactly like what you'd expect if briny water was seeping up from underground, flowing down slopes, and then evaporating or refreezing. Not everyone agrees that's what's happening. Some think it might be dry sand flows or CO2 frost doing weird things, but the water explanation fits pretty well. We've also got ground ground-penetrating radar data suggesting large deposits of water ice mixed with soil and possibly even liquid water layers at depth. One study claimed to find a lake of liquid water about 10 kilometers underground near the South Pole, though other scientists dispute that interpretation. So the picture of Mars we have now is dead on the surface, but potentially alive underneath, which makes it both frustrating and exciting. Frustrating because we can't just look around with our rovers and find life, they're stuck on the surface. Exciting because if life is down there, it's probably been down there for billions of years, evolving in isolation, following its own weird evolutionary path. Imagine what Martian cave life might look like. It's been separated from sunlight for eons, it's never seen a sun, doesn't know what photosynthesis is, it's living off chemistry alone, pulling energy from reactions between water and minerals, maybe using sulfur compounds or iron as energy sources instead of oxygen, and there's legitimate scientific work being done on how we'd explore this. Robot spelunkers, cave drones, machines that could descend into Martian cave systems, map them, sample the walls for biological activity. Some researchers are even identifying specific caves, actual openings on the surface that lead to underground networks, and saying these should be priority targets for future missions. Because here's the thing, if we find life on Mars, even just bacteria, even just fossil bacteria, it changes everything. It means life isn't unique to Earth. It means wherever conditions are remotely suitable, life tries to get a foothold. And if life is common, then maybe, just maybe, intelligent life isn't as rare as we fear. But Mars isn't the only place nearby that might harbor life. We need to talk about the planet everyone assumes is hell. Venus is the worst place in the solar system. Hands down, I will fight anyone who disagrees. Surface temperature, 460 degrees Celsius. That's 860 Fahrenheit, hot enough to melt lead, hot enough that our probes last about an hour before they literally cook to death. Atmospheric pressure, 90 times Earth's. That's the equivalent of being a kilometer underwater. Crushing pressure that will squash anything that isn't specifically engineered to resist it. The atmosphere itself, 96% carbon dioxide, and the clouds, concentrated sulfuric acid. Not diluted acid rain like we get from pollution on Earth. I'm talking drops of actual battery acid falling from the sky. Venus is what happens when a runaway greenhouse effect turns a planet into hell. And the terrifying thing is, Venus started out almost identical to Earth. Same size, same basic composition, same neighborhood around the sun, just slightly closer to our star, but that little bit of extra solar heating was enough. Water in the atmosphere absorbed more heat. More heat meant more evaporation. More water vapor, which is itself a greenhouse gas, meant more heat. More heat meant more CO2 released from rocks. More CO2 meant more greenhouse warming. Feedback loop, runaway process, and within a geologically short time, maybe a few million years, Venus went from potentially habitable to absolutely hellish. The oceans boiled away, the water vapor eventually got broken down by ultraviolet light into hydrogen and oxygen. The hydrogen escaped to space. The oxygen reacted with rocks, no water left, just a thick, hot, toxic atmosphere and a planetary surface that looks like what happens when you accidentally leave hell's oven on for a billion years. And this is why Venus matters to us. It's a warning. It shows us that Earth-like planets can tip into uninhabitable states. Climate scientists study Venus obsessively because it's an example of what happens when greenhouse warming goes completely off the rails. But here's where it gets interesting. In September 2020, a team of astronomers announced they detected phosphine in Venus's atmosphere. Phosphine, pH 3, phosphorus, and hydrogen. And on Earth, the only significant source of phosphine is life, specifically anaerobic bacteria, microbes that live in oxygen-poor environments like swamps and marshes. There are trace amounts produced by lightning and volcanic activity, but biological sources dominate, so if there's phosphine on Venus, maybe there's life on Venus. The detection was made using radio telescopes in Chile, some of the most sensitive instruments in the world, working at extremely high altitude where Earth's atmosphere is thin. They picked up the spectral signature of phosphine at an altitude of about 50 to 60 kilometers above Venus's surface. And that altitude is interesting because conditions up there are actually kind of tolerable. The pressure is about 1 atmosphere, Earth normal. Temperature is around 0 to 30 degrees Celsius, depending on exact altitude. The clouds at that level, while acidic, are dilute enough that some extremophile bacteria might handle them. So the hypothesis is maybe Venus has airborne life, microbes living in the cloud layers, floating in droplets of acid, metabolizing whatever chemical energy they can extract from their environment. never touching the hellish surface, just drifting in the relatively mild upper atmosphere forever. It's wild, it's speculative, and it might be completely wrong because here's the thing, the phosphine detection is controversial. Other teams have looked at the data and said, we're not sure that's actually phosphine. The spectral signature is ambiguous. It could be phosphine or it could be sulfur dioxide with some weird pressure and temperature effects making it look like phosphine. And even if it is phosphine, there might be non-biological ways to produce it that we haven't thought of. Weird atmospheric chemistry, lightning doing something unexpected, volcanic outgassing with unusual compounds. To really settle this, we need to go there, send probes that can sample the atmosphere directly, analyze the chemistry, look for actual evidence of life instead of just one ambiguous molecular signature. And guess what? We're going. There are 6 or 7 missions to Venus planned for the next decade. NASA is sending probes, ESA is sending probes. India, China, Russia, everyone wants a piece of the Venus action. Some will study the surface, trying to understand the planet's history. Others will focus on the atmosphere, looking for that phosphine and trying to figure out what's making it. If they find microbes floating in Venus's clouds, it'll be the second biggest discovery in the history of biology, the biggest being if we find intelligent aliens, obviously. But there's another world that might surprise us, one that nobody even considered until recently because it's so close to the sun that it should be completely dead. Let's talk about Mercury. Mercury, the closest planet to the sun. You'd think it would be nothing but a scorched, dead rock, right? And mostly you'd be right. Daytime temperature on Mercury's surface, 430 degrees Celsius, hot enough to melt zinc. Nighttime temperature, negative 180 degrees Celsius, cold enough to freeze carbon dioxide solid. The temperature swings are more extreme than anywhere else in the solar system because Mercury barely has an atmosphere. Just a thin exosphere of atoms knocked off the surface by solar wind. No air means no heat distribution. No heat distribution means the day side cooks and the night side freezes, with nothing in between, so obviously no life. Case closed. Move on. Except, what about underground? Radio astronomers measured the subsurface temperature near Mercury's equator and found something surprising. About a meter below the surface, the temperature is around 67 degrees Celsius. That's 152 degrees Fahrenheit. Hot, but not that hot. People sit in saunas at 80 degrees Celsius and survive. Many microorganisms thrive at 67 degrees. Some extremophiles prefer it. Go further from the equator toward mid-latitudes, and the subsurface temperature drops to around 20 Celsius. That's room temperature, literally t-shirt weather. Near the poles, it gets cold, below freezing, but some bacteria love the cold too. So from a temperature perspective, Mercury's subsurface environment spans the entire range of habitable temperatures. You could find a zone underground that's perfectly comfortable for whatever your preferred temperature range is. Okay, you say, but there's no water, no organics, nothing to build life from. Well, maybe. Here's where it gets weird. When spacecraft photographed Mercury in detail, they found something strange. Certain impact craters have abnormally dark floors, not gray like the surrounding rock. Black, really black, almost no light reflection. And the material looks organic. Spectroscopically, it's similar to the complex organic tars and hydrocarbons we find in carbonaceous meteorites, dark carbon-rich compounds. On Earth, black organic-rich deposits usually mean one thing: life. Dead life that's been cooking underground for millions of years, but life nonetheless. We call it oil or coal or kerogen. Could Mercury have something similar? Could there be or have been subsurface microbial life producing organic compounds that occasionally get exposed on the surface? Retry H continue when meteorite impacts punch through and excavate the deep layers? It's extremely speculative. Most scientists think those dark deposits are probably just carbon-rich material delivered by meteorite impacts over billions of years. Mercury has been taking hits from comets and asteroids its entire existence, and many of those objects are rich in organic compounds. Smash enough of them into Mercury's surface and you'd get dark carbon stains in crater floors. But the alternative is tantalizing. What if there's a subsurface biosphere on Mercury? What if microbial life exists in thermal zones underground, metabolizing whatever chemical energy is available, and those black patches are the waste products or dead remnants of that life? We won't know until we go there, and going to Mercury is hard. It's deep in the sun's gravity well, which makes it expensive to reach. The radiation environment is brutal. You're that much closer to the sun's output. Only 2 spacecraft have ever visited, Mariner 10 in the 1970s and Messenger in the 2010s. Neither landed, they just flew by and took pictures. 1. To really investigate those black deposits, we'd need a lander with drilling equipment and a sophisticated chemistry lab. We'd need to sample material from different depths and analyze it for biological signatures. That's probably decades away if it happens at all. But the mere possibility that Mercury, the closest planet to the Sun, might harbor subsurface life, that's mind-blowing. It would mean life can get a foothold in the most unlikely places, which brings us to what might be the most promising locations in the entire solar system for finding life, the ice moons. And these aren't at Mercury's distance from the Sun. They're way out in the cold, dark outer solar system, which should make them dead and frozen, should being the operative word. Jupiter has dozens of moons. Most are just captured asteroids, small, irregular chunks of rock, but 4 of them are massive, roughly the size of our moon or larger. Galileo discovered them in 1610, and they're called the Galilean moons, Io, Europa, Ganymede, and Callisto. Io is a volcanic nightmare, the most geologically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the place. Ganymede and Callisto are big ice balls with interesting geology, but probably not life. But Europa is special. Europa is covered in ice, thick ice, maybe 20 kilometers deep in some places, and the surface looks weird. It's crisscrossed with cracks and ridges, stained with brown and red discoloration, relatively few craters. It looks young, it looks active, and beneath that ice shell, an ocean, a global ocean of liquid water, possibly 100 kilometers deep. We know this because of magnetometry. When spacecraft fly by Europa, they can measure the magnetic field around it, and Europa has a weak magnetic field that appears to be induced, created by Jupiter's powerful magnetic field interacting with something electrically conductive in Europa's interior. Salt water is electrically conductive, freshwater ice is not, so Europa must have a salty liquid ocean underneath that ice. The heat to keep that water liquid comes from tidal flexing. Europa's orbit around Jupiter isn't perfectly circular, it's slightly elliptical. As Europa gets closer and farther from Jupiter, the tidal forces squeeze and stretch the moon. That flexing generates heat through friction in Europa's interior, the same way bending a paperclip back and forth makes it hot. So you've got a 100-kilometer deep saltwater ocean kept liquid by tidal heating, protected from Jupiter's radiation by 20 kilometers of ice, potentially sitting on a rocky seafloor where hydrothermal vents might exist. Sound familiar? It's basically the same environment as Earth's deep ocean, and we've found thriving ecosystems around hydrothermal vents in Earth's deepest, darkest ocean trenches. No sunlight? Doesn't matter. The organisms at those vents don't use photosynthesis. They use chemosynthesis, extracting energy from chemical reactions between hot vent water and cold seawater. The chemistry provides the energy, and entire food chains build from there. We've found tube worms, crabs, fish, octopuses, bacterial mats, whole ecosystems that have never seen the sun and don't care. If Europa has similar vents on its seafloor, and the geology suggests it might, then Europa could have similar ecosystems. Maybe not fish and crabs, but bacteria for sure, maybe more complex organisms. Who knows how far evolution might have gone in Europa's ocean over the past 4 billion years? And here's the exciting part. We don't necessarily have to drill through 20 kilometers of ice to find out. Europa has geysers. The Hubble Space Telescope has photographed plumes of water vapor shooting up from Europa's surface, geysers erupting through cracks in the ice, spraying ocean water into space. Some of it falls back as snow, but some of it forms a thin atmosphere, and some might carry organic material or even microorganisms from the ocean below. 2 missions are currently on their way to Jupiter to study Europa up close. NASA's Europa Clipper launched in 2024, and ESA's JUICE, Jupiter Icy Moons Explorer, is also en route. They'll arrive around 2030 to 2031. These aren't landers, they're orbiters that will make multiple close flybys of Europa, swooping low over the surface, flying through those geyser plumes if possible, using spectrometers and mass spectrometers to analyze whatever they encounter. If there are organic molecules in those plumes, amino acids, lipids, anything that suggests biological activity, the instruments should detect them. If there are actual microorganisms being ejected from the ocean, well, that would be the discovery of the millennium. And Europa isn't alone. Saturn's moon Enceladus is similar, smaller, but also has a subsurface ocean and active geysers that we've already flown through with the Cassini probe. And Saturn's largest moon, Titan, has liquid methane lakes on its surface and possibly a subsurface water ocean too. The outer solar system is apparently full of hidden oceans. We went from thinking life needs an Earth-like planet with sunlight and a surface surface ocean to realizing that icy moons with underground seas might actually be more common and potentially more habitable. If we find life in Europa's ocean, even just bacteria, it would prove that life can arise independently in isolated environments. It would mean life isn't a fluke that happened once on Earth. It would mean the universe might be teeming with life in places we never thought to look. But what about worlds beyond our solar system? What about actual exoplanets around other stars? Have we found any signs of life there? As of a few days ago, we've discovered about 7,900 exoplanets. That number is growing almost daily. Most of them are giant gas planets like Jupiter. Those are easier to detect. But we've also found dozens that are roughly Earth-sized, rocky, and orbiting at distances where liquid water could exist. Finding them is one thing. Figuring out if they have life is another thing entirely. See, these planets are light years away. We can't send probes. We can barely see them directly. Most are detected by indirect methods like watching their star dim slightly when they pass in front of it or measuring the star's wobble from the planet's gravitational pull. But we can analyze their atmospheres using spectroscopy. When a planet transits in front of its star, some of the starlight passes through the planet's atmosphere on its way to us. Different molecules in that atmosphere absorb light at specific wavelengths, creating a sort of chemical fingerprint. By analyzing that fingerprint, we can determine what gases are present in the atmosphere, and certain gases are biosignatures, molecules that, on Earth at least, are primarily produced by life. Oxygen is a big one. Earth's atmosphere is 21% oxygen, and almost all of it comes from photosynthetic organisms. Without plants, algae, and cyanobacteria constantly producing oxygen, it would react with rocks and disappear within a few million years. So if you find a planet with lots of oxygen in its atmosphere, that's a hint, not proof. There are theoretical ways to produce oxygen without life, but a strong hint. Methane is another. As we discussed with Mars, methane is produced by life on Earth, though it can also come from geological sources. But the really interesting biosignature is something called dimethyl sulfide, DMS. It's the molecule that makes the ocean smell like the ocean, that distinctive sea breeze scent when you walk toward a beach. That's dimethyl sulfide. On Earth, DMS is produced almost exclusively by marine phytoplankton, microscopic algae floating in the ocean. When they metabolize certain sulfur compounds, they release DMS as a byproduct. It's a very specific biosignature with very few non-biological ways to produce it. And in 2023, the James Webb Space Telescope detected what might be dimethyl sulfide in the atmosphere of an exoplanet called K218b. K2-18b is about 120 light-years away in the constellation Leo. It's roughly twice Earth's diameter, a super-Earth or mini-Neptune depending on how you classify it, and it orbits its star at a distance where temperatures should allow liquid water. Webb's instruments detected water vapor in the atmosphere, lots of it. That alone is interesting, but buried in the spectral data is a possible signal for DMS. Possible? Maybe. The detection isn't confirmed, the spectral line is weak and could be confused with other molecules. No other telescope can verify it because nothing else is sensitive enough. But if it's real, if K2-18b actually has dimethyl sulfide in its atmosphere, then something on that planet is producing it, and the most likely something is life, ocean life, floating in a global ocean, doing its biological thing, occasionally burping out DMS. The scientific community is being very cautious about this. The lead researchers are saying we detected a possible tentative maybe signal that could potentially be DMS if our analysis is correct and nothing else is mimicking it. They need confirmation. They need other instruments to look at the same planet and either confirm or refute the detection. Webb is going to observe it again with different instruments. And in a few years, other advanced telescopes will come online that can provide independent verification. But imagine if it's confirmed. Imagine if we can definitively say there is a planet 120 light years away and it has an ocean, and something in that ocean is producing biosignatures. We wouldn't know what that something is. Could be bacteria, could be algae, could be something completely alien that we can't even imagine. But it would be life, unambiguous, confirmed life on another world. That would change everything. It would answer one of the most fundamental questions humans have ever asked. Are we alone? And the answer would be no. Of course, detecting biosignatures isn't the same as detecting intelligence. Finding microbes on Mars or algae on K2-18b doesn't tell us anything about whether intelligent civilizations exist. For that, we need a different kind of search. Search for extraterrestrial intelligence. For over 60 years, we've been listening for radio signals from other civilizations, and for over 60 years, we've heard nothing. Silence, just the random hiss and crackle of natural astronomical radio sources. Yuri Milner, Russian-Israeli billionaire, physicist by training, tech investor by profession, decided that SETI needed a serious cash infusion. In 2015, he launched Breakthrough Listen with a $100 million budget. That's more money than all previous SETI efforts combined over the previous 5 decades. That money bought time on the world's most powerful radio telescopes, the Parkes Telescope in Australia, the Green Bank Telescope in West Virginia, and most importantly, China's FAST Telescope, 500 meters across, the largest single-dish radio telescope on Earth. The idea is simple. Scan millions of stars, billions of radio frequencies, looking for patterns that can't be natural, a narrow bandwidth signal that drifts in frequency as a planet rotates, a pulse pattern that repeats too regularly, anything that screams artificial. They've been running for almost a decade now. They've collected petabytes of data. They've detected thousands of interesting candidate signals, and every single one, after careful analysis, turned out to be human interference. Satellites, radar, random electronics, terrestrial transmitters bouncing signals in unexpected ways. Nothing confirmed extraterrestrial, not yet. But here's the thing, radio might not be the right approach. We use radio for long-distance communication, sure, but we're increasingly moving to optical fiber, light, not radio waves. Information transmitted as photons through fiber optic cables is faster, higher bandwidth, more secure than radio. If we're making that transition, maybe advanced civilizations did too. Maybe they used radio for a brief period, a few hundred years, and then switched to something better. And we're trying to listen to their radio transmissions during the narrow window when we have radio technology, but they've already moved on. Some researchers think optical SETI is more promising, looking for laser pulses instead of radio waves. A powerful laser can be focused into a tight beam that travels across interstellar distances without spreading out too much. It's high bandwidth, it's efficient, and here's where Russia comes in again, but this time with a project that costs almost nothing. Near Lake Baikal in Siberia, there's a facility run by Moscow State University's Institute of Nuclear Physics. They've built an array of detectors designed to catch cosmic rays, high-energy particles from space that hit Earth's atmosphere and create brief flashes of light. One of the researchers, a guy named Panov, realized these detectors are looking for flashes of light from space. What if we're accidentally catching laser signals from aliens and just ignoring them because we think they're cosmic rays? So they started running pattern-matching algorithms on the data, looking for signals that might be artificial. Pulses that repeat, patterns that encode information, anything weird. They've been doing this for 3 years now. They've caught satellite laser altimeters, instruments on Earth-orbiting satellites that use lasers to map terrain. They've caught atmospheric phenomena. They've caught all kinds of terrestrial noise, but no confirmed alien laser signals, not yet, though Panov points out maybe they have detected alien signals, but they just don't recognize them as such. If you don't know what you're looking for, how do you know when you found it? So let's say we detect something, a radio signal, a laser pulse, an unambiguous message from another civilization. What do? We can't exactly hop in a spaceship and go meet them. Interstellar distances are vast. The closest star system to us is Alpha Centauri, about 4.4 light years away. That sounds close in cosmic terms, but in practical terms, it's absurdly far. Our fastest spacecraft, the Voyager probes, are traveling at about 17 kilometers per second. At that speed, it would take about 75,000 years to reach Alpha Centauri. Not exactly a quick trip, but Yuri Milner, yes, him again, has an idea. It's called Breakthrough Starshot, and it's simultaneously brilliant and insane. The concept, build a fleet of tiny spacecraft, each about the size of a postage stamp, weighing a gram or less. Attach each one to an ultra-thin reflective sail, maybe 3 to 4 meters across, but weighing only a gram or two. Total mass per craft, a few grams. Then build a massive array of ground-based lasers, we're talking gigawatts of laser power, and aim them all at the sail. The photon pressure from the laser light pushes the sail, accelerating it because the craft is so light, it doesn't take much force to accelerate it. Within a few minutes of laser illumination, the craft reaches about 20% the speed of light. Then you turn off the lasers and let it coast. At 20% light speed, you reach Proxima Centauri in about 20 years. Add another 4 years for the radio signal to come back, and you get data from another star system in about 24 years. That's within a human lifetime. Kids born today would see the results before they retire. Is this crazy? Absolutely. Is it technically feasible? Maybe. There are enormous engineering challenges building a sail that's reflective enough, light enough, and strong enough to handle the acceleration without tearing. radiation. Building lasers powerful enough to push something to 20% light speed, that's a lot of energy. Aiming those lasers accurately enough to hit a meter-scale target for several minutes while it's accelerating away from you, protecting the electronics from the intense laser heating and the radiation environment of interstellar space, sending back data from 4 light years away using a transmitter the size of a grain of rice. Every one of those is a hard problem, but none of them violate physics. It's engineering, not magic. Milner has apparently put $100 million into initial research, and there are actual peer-reviewed papers from reputable scientists saying, yeah, this could work. The target would probably be Proxima Centauri b, an Earth-sized exoplanet orbiting Proxima at a distance where liquid water could exist. We don't know much about it beyond basic stats, but it's the closest potentially habitable world we've found. A gram-sized probe obviously can't carry much instrumentation, but it could have a camera, maybe a simple spectrometer, enough to take pictures, analyze atmospheric composition, and beam the data back home. And here's the beautiful part: because the craft is so cheap and light, you don't send just one, you send thousands, entire fleets of them. If 90% fail due to laser targeting errors, micrometeor strikes, or equipment failures, you still have hundreds that make it. Will this actually happen? I don't know. The technical challenges are immense. The funding required beyond the initial research phase is substantial, but it's not impossible. And if someone like Milner is willing to put up serious money, and if universities and research institutions are willing to contribute expertise, we might actually get pictures from another star system within our lifetimes. How crazy is that? Okay, let's bring this back to something more immediate. Forget exoplanets 120 light years away. Forget light sails to Proxima Centauri. When are we actually going to Mars? When will humans set foot on another planet? The realistic answer, based on current technology and trajectories, is somewhere between 2032 and 2035. Why then? Because of SpaceX's Starship. Say what you will about Elon Musk, and people say a lot, but Starship is real, it's flying, and it's getting better with every test. It's designed from the ground up to be a Mars transport, fully reusable, enormous payload capacity capable of refueling in orbit, designed to land vertically on unprepared surfaces. NASA has their own plans with the SLS rocket and Orion capsule, but those are primarily focused on the moon. China is developing heavy lift capabilities, but they're a few years behind. Russia talks a big game, but doesn't have the budget. ESA does great science, but isn't pursuing human Mars missions independently. So yeah, it's probably going to be Starship, which means the timeline depends on when Starship is ready for prime time. Currently, Starship is doing suborbital and orbital test flights. Some succeed, some explode, that's how testing works, but they're iterating fast, like multiple launches per year. Within 2 years, they'll probably have it reliable enough for cargo missions, another year or two for crewed orbital flights, then lunar missions to prove out the life support and long-duration systems by the early 2030s. A Mars mission becomes technically feasible. Now, that's not a quick surface visit. You can't just fly to Mars, plant a flag, and fly home. The orbital mechanics don't work that way. Earth and Mars line up favorably for transfers about every 26 months. If you go to Mars, you're stuck there for a while, probably 18 months, waiting for the planets to align again for the return trip. So the first Mars mission will be long duration, probably 30 months total, 6 months travel to Mars, 18 months on the surface, 6 months back. That's longer than any space mission in history. The longest anyone has stayed in space is about 14 months on the ISS. This will require testing, probably a long-duration lunar mission first, proving that humans can live in isolated, hostile environments for extended periods. Maybe a Mars orbit mission, go to Mars, orbit for a while, come back without landing just to prove the spacecraft and systems can handle the journey. But eventually, someone's going to step onto Mars. What will they do there? Initially, just survival, setting up habitats, deploying solar panels or nuclear reactors for power, figuring out water extraction. There's ice in the soil, you just have to heat it. Growing food, greenhouses with Martian soil supplemented with nutrients. Exploration comes later, driving rovers to interesting locations, drilling into the surface, hopefully finding those caves we talked about and sending robots inside to look around, establishing a permanent base. That's further out. That requires regular cargo missions, probably building habitats underground for radiation protection, setting up industrial capabilities, making fuel, making building materials from local resources, full terraforming, transforming Mars into an Earth-like world with breathable atmosphere. atmosphere is probably impossible. Mars just doesn't have enough nitrogen to build an Earth-like atmosphere, and it doesn't have a strong magnetic field to protect that atmosphere from solar wind stripping. But localized habitable zones, living in pressurized underground cities with surface access, that's doable. That might even be desirable. Mars gravity is 38% of Earth's, which is much easier on the human body than 0G. The day length is almost identical to Earth's. The environment, while harsh, is manageable with technology we either have or can develop. So yeah, 2032, 2035 for first human boot prints, maybe 2040s for a semi-permanent research station, 2050s and beyond for actual settlement. We're not that far away. Some of you listening to this will live to see humans walking on Mars. That's kind of amazing when you think about it. All right, let's zoom out, way out. Let's talk about what all of this means. We've covered a lot of ground here: mysterious interstellar visitors that might or might not be alien probes, evidence for microbial life possibly existing on Mars, Venus, Mercury, and the ice moons, exoplanets with potential biosignatures, SETI searches coming up empty, plans to reach nearby stars within decades. What's the through line? What's the big picture? I think it's this. We're at a weird moment in human history. We're technologically advanced enough to ask profound questions about life in the universe, but we're not quite advanced enough to answer them definitively. We can detect atmospheric chemistry on planets 100 light years away, but we can't say for certain if that chemistry indicates life. We can identify underground water on Mars, but we can't drill down and sample it. We can theorize about life in Europa's ocean, but we won't have direct evidence for another decade. We're tantalizingly close to answers, but not quite there yet. It's frustrating, it's exciting. It's like being a kid on Christmas Eve. Yeah, you know presents are coming tomorrow, but you have to wait. And here's the philosophical weight of it all. Every search for life elsewhere is also a meditation on the rarity and value of life on Earth. If we find life on Mars or Europa, even just bacteria, it means life is common. It means wherever conditions are remotely suitable, life finds a way. And if life is common, then statistically, intelligence probably arises sometimes, which means the universe might be full of civilizations and we just haven't met them yet because space is really, really big. But if we don't find life, if we search the solar system thoroughly and come up empty, that means life is rare, maybe incredibly rare. Maybe Earth is a fluke, a 1 in a trillion chance, and we're essentially alone in the observable universe. And if we're alone, then the responsibility to preserve and protect life becomes even more profound. Because if Earth is the only place in the universe where life exists, and we screw it up through war, environmental destruction, asteroid impact, whatever, then we've extinguished the only light in an otherwise dark cosmos. That's heavy, that's existentially significant in a way that transcends politics or economics or any normal human concern. This is why scientists get passionate about this stuff. It's not just curiosity, though curiosity is part of it. It's the sense that these questions matter in the deepest possible way. Are we alone? If not, where is everybody? If we are alone, why? What does that mean for our future? These are questions that humans have asked since we first looked up at the stars and wondered. And for the first time in history, we might actually get answers within a generation or two. The telescopes are getting better, the spacecraft are getting more sophisticated, the detection methods are improving. Within your lifetime, yes, yours, listening to this, will probably know whether life exists elsewhere in our solar system. We might even have strong evidence for life on exoplanets. And if we don't find any, that's an answer too, a sobering one, but an answer. Either way, we're living through a pivotal moment in human history, the moment when we transition from wondering if we're alone to actually knowing. That's why Avi Loeb's work matters, even if he's wrong about Oumuamua and Atlas being alien spacecraft. He's asking the right questions, even if his answers are premature. He's forcing the scientific community to confront possibilities they'd rather dismiss. That's why Mars exploration matters, why Europa Clipper matters, why the James Webb Telescope matters. We're building the tools and acquiring the knowledge to finally answer these fundamental questions. And whether you're a believer in aliens, a skeptic, or somewhere in between, you have to admit we're living in interesting times. The cosmic visitors, whether they're just space rocks or something more, are reminders that we're part of a larger universe, that Earth isn't isolated, that we're one planet among billions, orbiting one star among hundreds of billions, in one galaxy among trillions, and somewhere out there, maybe something else is looking up at their sky and wondering the same things we're wondering, or maybe not. Maybe it's just us alone with our questions and our curiosity, trying to understand our place in an empty cosmos. Either way, we keep looking, we keep searching, because the questions are too important not to ask, and the answers, whatever they turn out to be, will shape humanity's understanding of itself for generations to come. That's why this matters. That's why we care about weird cigar-shaped objects flying through our solar system, about methane on Mars, about phosphine on Venus, about oceans under ice on distant moons. We're not just exploring space, we're exploring the biggest question humans have ever asked. Are we alone? And someday soon we might finally know. 1.